Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. We are still in the network layer chapter. In the previous video, we talked about some basics related to the network layer. We talked about connection-oriented services and connectionless services. In other words, we talked about virtual circuits and datagrams. And for each one of these two cases, we talked about the structure of the routing tables involved. And we talked about how routers use these routing tables to make forwarding decisions. In other words, how do routers use these tables to decide how they will forward the packet? What is the next hop for an incoming packet? Now, in this video, we would like to talk about the routing algorithms. Having mentioned routing algorithms, let's distinguish first between packet forwarding and a routing algorithm. When we say packet forwarding, what we mean is basically the router using a routing table similar to the ones that we mentioned last time. A router using a routing table like this kind of table for connectionless services. A router using such a routing table to decide what is the outgoing link for an incoming packet. So using the table, the router will check basically the destination of the packet, and then based on the information in that table, the router is able to decide how to forward the packet. This is what we call packet forwarding, using of the routing table so that the router decides how to forward the packet. Now, a routing algorithm is really responsible for updating the routing tables. How do the routers come up with these tables in the first place? How do the routers come up with these tables so that they reflect the best paths or the optimal paths in the network in the first place? And how are these tables updated periodically so that we keep track of the best paths as these paths change according to the network conditions? This is what we call a routing algorithm. Just as a reminder, if we are having a virtual circuit service, like in a connection-oriented services, a routing decision is made whenever a new virtual circuit needs to be set up. So at the beginning of the virtual circuit, when we have a new virtual circuit request, when we need to establish a new connection or a new virtual circuit, we have to choose a path at that time, and then this path will remain fixed for all the packets that belong to this virtual circuit. So once at the beginning of the virtual circuit. However, in datagram networks, in connectionless services, different packets may take different paths. So forwarding decisions are basically made for each packet individually. And routing algorithms are applied periodically so that the routing tables are updated from time to time, typically every 30 seconds or so in the current internet. Now, we need to be defining the meaning of routing optimality. What is the notion or the meaning of routing optimality? When we say an optimal route or an optimal path, we say the best path. However, we need to define best in what sense? Best from which objective point of view? Is this is the path that minimizes the delay? Is this is the path that maximizes the network throughput? Is this is the path that maximizes the amount of information per second that can be pushed into the network? Is this is the path that minimizes the number of hops, like the number of links that constitute to this path? So as you notice, we could use different objectives to come up with a path, and depending on which objective we use, we could have a different optimal path. So when we say optimal path, we have to know exactly what is the objective being used. In the current internet, we stick to shortest paths, right? Shortest or the least distance path. However, let's finish talking about it first, and then you will also realize that this is a general notion. So even though we say shortest, but this notion captures different objectives, basically. So let's wait until we get there. However, what we want to talk about in this slide is the optimality principle. So what is the optimality principle? And as you will notice, it's a very important principle that will allow us to come up with very intelligent and very efficient algorithms that can provide the best path or the shortest path from a given source to a given destination. So what is the optimality principle? I think it is best that I use my own illustrative slide here. The optimality principle says the following. Imagine that this is router I and this is router K, and this path from router I to router K, that path indicated on the figure, is a path from router I to router K. It is not just a path from router I to router K, it is given to us that this is the shortest path from I to K. So it is a known fact, it is given to us that this path, which is shown in the figure, is the shortest path from I to K. In addition to this, it is given to us also as a fact that this path from I to K passes by some router J. So what is this router J? Router J is an arbitrary router which lies on this shortest path from I to K. Now we have a question. The question is the portion of the path. This is again the path from I to K, and we know that this path from I to K is the shortest possible path from I to K. There does not exist any other path from I to K which is shorter from the one shown, and this is a fact given to us. Now the question is that portion of this path from J to K. So starting from J, following the same path until we reach K. That portion of the given path from J to K, is this the shortest possible path from J to K, or is there any other path from J to K which is different from this one? This is the question. Now the answer is yes. That path from J to K along the original path from I to K is the shortest possible path from J to K. There is no other alternative path from J to K which is shorter than this portion of the original path from I to K. Can we prove this? Yes, actually we can prove it really simply using a technique called proof by contradiction. To prove something by contradiction, imagine that we have a fact that we need to prove. Proof by contradiction starts by assuming that this fact is not true. We start by assuming that the fact we want to prove is not true. Assume it is not true. If this assumption leads to a contradiction, if this assumption leads to something impossible, then it should have been the case that the fact is true. And that's how we prove a fact by contradiction. Let's focus on how we do it for this question here. So question again, to simplify things again, the path shown is the shortest possible path from I to K. That path goes through some router J. So let's call the first portion of the path from I to J, let's call it R1, and the second portion of the path from J to K, let's call it R2. So what is given to us as a fact? That R1 and R2 combined, R1 and R2 combined is the shortest path from I to K. The question is this portion R2 itself. This portion R2 itself, is it the shortest possible path from J to K? The answer is yes, right? So the fact, the optimality principle that we would like to prove is that R2 is the best possible path, is the shortest path from J to K as well, and this is what we would like to prove by contradiction. How can we prove it by contradiction? We start by assuming that R2 is not the shortest path from J to K. If R2 shown here, this is R2, which is part of the bigger path from I to K. If this R2 is not the shortest from I to K, what does this imply? It implies that there is a shorter path, that there is a path from J to K shorter than R2. Let's call this path R3. There exists a path from J to K. Let's call it R3 in general, which is shorter than R2. So the distance of R3 is shorter than the distance of R2. Now, if this is true, that we have some path from J to K, which is shorter than the path R2, what could we have done? We could have combined R3 with R1 so that we provide a path from I to K, which is shorter than R1, R2. So basically R1 combined with R3 would have been shorter than R1 combined with R2, and this is a contradiction. Why is this a contradiction? Because it was given to us that R1, R2, this particular path from I to K going through J is the shortest path from I to K, which means that there is no other path shorter. So bottom line, what we have just proved here, what we have just proven here is that this portion from J to K along the original path is the shortest path as well between J to K. Actually, this can be extended as well. We can say the following. If the shown path here from I to K is the shortest path, if this path is the shortest path from I to K, then any portion along this path is also a shortest path. So that part from this router until the destination is also the shortest path. And that portion from this router to the destination is also the shortest path, and so on. So if we have a shortest path, we have a lot of other shortest paths as a byproduct, and this helps a lot in coming up with an actual algorithm to find the shortest path from a given source to the given destination. And that algorithm that we will study is called the Dijkstra shortest path algorithm. Dijkstra is the name of the person who invented this algorithm quite long time ago. So it's a well-known algorithm even from computer science, and that's why to talk about this algorithm, we would like to talk to you a little bit about the fact that a network, a communication or a computer network, can be represented as a graph. So what is a graph in computer science? A graph is a structure like this. A graph consists of nodes interconnected by links, right? That graph can mean many things. For us in this course, that graph represents a computer network. So a node in the graph represents a router in the communication network, and a link in the graph represents an actual communication link in the communication network. But in computer science, graphs can be used in many other applications. So imagine that we have phenomena basically that interact with each other. So this is a phenomena and this is another phenomena. If these phenomena are related, then they have a link interconnecting them. So what we wanted to say is that graphs are more general than computer networks. To talk about routing algorithm, to talk about shortest path routing algorithms, an actual algorithm that can be used to obtain the shortest path between a source router and a destination router, what we do is that we represent the network as a graph, right? A network is represented as a graph, which is something very natural. The network looks like a graph anyway. So a node in this graph represents a router in the network, and the link in the graph represents a communication link. In addition to this, do you see these numbers? These numbers represent weights for the links. So these numbers, that number 2 and this number 7 and this number 4 and this number 3 and so on, these numbers could be representing the distance of the links. However, they could be also representing the delay of the links. So what is the delay for a packet to start from A until it arrives at B and so on? So it could be the actual physical distance, it could represent the delay, and it could represent some other things. So for simplicity now, let's just assume that these numbers represent distances or weights, right? So what is the question here? The main question, given a network represented by a graph as the one that you see here, given a source node, which is assumed to be A in the example, and a destination node, which is assumed to be D in the example, the question is, what is the shortest path? What is the path that has the total shortest distance, that has the shortest total distance from the source to the destination? As you notice, we have a lot of alternative paths. So this is one possibility here, A, B, C, D, 2 plus 7 plus 3. This is basically 10, 12, so the total distance of this path is 12. Another alternative path is from A to D, from A to G to H to D, and the total distance is also 12. And maybe we have some other alternative paths. This is an alternative path, right? So 6 plus 1 is 7, plus 2 is 9, plus 2 is 11, plus 2 is 13. So this path is even longer. Now the question is, what is the shortest path from A to D? And the algorithm that we will cover is called the Dijkstra shortest path algorithm. Again, Dijkstra is the name of the person who has invented this algorithm, Dijkstra, right? He's Dutch from Holland, so we say Dijkstra, right? And the algorithm, this is what we will explain in the rest of this video. So as we said, given a network which is represented as a graph, so the graph has a source node, a source router, a destination node or a destination router, and the question is find the shortest path from source to destination. Of course, the shortest path will go through some of these links, and the objective is to find the path that has the shortest possible total distance. I've just convinced you that we have a lot of alternative paths that we can choose from. So we just tried this one on top, and we tried this one in the bottom, and we tried another alternative path that goes through the middle. And as you have noticed, these paths have different distances, they have different lengths. So how can we come up with the shortest one? make no mistake, what we will not be doing is to come up with all alternative paths and then choose the shortest one. This is what we cannot do. Of course, if we have a bigger network, this network maybe has a few nodes, maybe it is possible to enumerate all possible paths and then we choose the shortest one just by inspection. What I just described here is called exhaustive search. So in algorithms, this is called exhaustive search, or a brute force algorithm in which we try all possibilities and then we choose the best. We cannot do that, obviously, if you have tens, hundreds, thousands, hundreds of thousands of nodes. It is impossible to enumerate all possible paths because we have too many of them. We just have too many of them. So the question is, can we find the shortest path from the source to the destination using a systematic approach? The answer is yes. We have algorithms, systematic algorithms that avoid exhaustive search, systematic algorithms in which we don't have to enumerate all possible paths. We just apply systematic steps until at the end we find the shortest path from the source to the destination. One of these algorithms, in fact, one of the most famous ones is called the Dijkstra shortest path algorithm, and this is what we would like to explain. Now, the best way to explain the Dijkstra shortest path algorithm is using the example right away. So the graph that you see here is the same graph as in the slide, and I would like to show you how we come up with the best paths, the best path from A to D. And as you will notice that as a byproduct, we're not just finding the path from A to D, but as a byproduct, we can find the best path or the shortest path from A to B, from A to C, from A to D, from A to E, and so on. So basically, by applying this algorithm once, we can come up with the shortest path from a given source node. So we have a fixed source node, and the algorithm will return a set of paths, the shortest from A to B, and the shortest from A to C, and the shortest from A to D, and so on. So how does this algorithm work? The first step in applying this algorithm is to basically give each node a label, right? What you see here are the initial labels. However, to understand the meaning of these initial labels, we have to understand the meaning of the label itself. So imagine, without loss of generality, this is node F here. So if this is node F, and sometime along the application of the algorithm, node F here has a label which says 6, E. So as you notice, this label here, every node label, any node label has two entries, a number and the letter. The number represents the shortest, the distance of the shortest path known so far from the fixed source until the node. Again, if this is the label for node F, then this number, which is, as an example here, 6, assuming that it is 6, it means that the distance, the total distance of the shortest path discovered so far, right? Maybe we will come up with better paths, but as far as we have discovered the distance of the shortest path discovered so far from the fixed source node to the node here that we are labeling is 6. What about the second entry? The second entry is the node before F along this best path. So where is this shortest path coming from? Again, if we're talking about node F and the label of node F is 6, E, and this is what we know so far. What this means is that the total distance of the shortest path from the fixed source until our node has a distance of 6. The shortest path discovered so far from the fixed source until our node that has a label is 6 in this example, and the node previous to me along this path is E. So where is this path coming from? It is coming from E. So the label contains the distance, basically, of the shortest path discovered so far from the fixed source, and also where is this path coming from? What is the previous node along this path? Now, since at the beginning I still don't know any path, this means that we have to initialize all these labels to be infinity. So what is the label at B here? Infinity, comma dash. What is the total distance of the shortest path from the source to B? I don't know it yet, so it's infinity. Where is it coming from? I don't know, so it's just an empty label dash. So infinity, comma dash, infinity, comma dash, infinity, comma dash, infinity, comma dash, and so on. This is the initial label for every node in the network, right? However, we are assuming that we have one particular node which is being used as the source. So the source is given. The question here, what is the shortest path from A to D? Or equivalently, what is the shortest path from A to everybody else? Bottom line, we have a fixed source and it is A in this example. So how do we start the algorithm? How do we start Dijkstra shortest path algorithm? We start by giving each node an initial label, and that label is infinity comma dash for every node. Now, what do we do next? We stand here. Do you see this arrow? That's what we do next. We stand at the source node and we investigate the neighbors. Who are the neighbors of A? The neighbors are those nodes who are directly connected to the source, which is B and G. Let's investigate how far these nodes are. So B, how far is this node B? It's a distance of 2 because we have a direct link. So we know that B is at a distance of 2 because we have just investigated this direct link. And since 2 is less than infinity, so that label that was infinity, let's change it. Let me change color here. So that label becomes 2 comma A, which means that we have just discovered a path to B. That path is coming from A because I was standing here at A. That's my arrow. This is my permanent node, right? This is my permanent node, and the source is the initial permanent node. I'm standing there, and I'm examining the neighbors, and I'm possibly updating the labels. Please concentrate and focus with me. I'm standing at the initial source node. I'm examining the neighbors, possibly updating the labels. So the actual distance from A to B is 2 because I have a link that has a distance of 2. So the new label becomes 2 comma A. So the best path discovered so far until B has a distance of 2 and it is coming from A. I'm standing here, so it's coming from A. What about G here? G has a distance of 6 because this link has a distance of 6. So that infinity will get updated, right? So 6 comma A. Now this is the new label at router G. What does this label mean? This label means that the shortest path discovered so far from the fixed source until router G has a total distance of 6, and it is coming from A directly because I was standing here at A. So this is the first step. I stand at the source node. I stand at the source node. It's marked as permanently labeled because I stood here already. I put an arrow. I stand and then I check the neighbors only. I check the neighbors only and I update the labels. When do I update the label? When do I take out a label and replace it with a new one? If the new label has a smaller value, because I'm looking for the shortest path at the end. If the new label has a smaller value than the existing label, since we are only at the initial step and all existing labels are infinity, so if I find any label that has a finite value, it's definitely better. So that infinity will be taken away and I'm standing at the next node. Now, what is the next step? So this is the first step. I stand at the source, I check the neighbors, I've updated the labels. So the infinity comma dash that belongs to node B was changed to 2 comma A, and the infinity comma dash that belongs to node G was changed to 6 comma A. What is the next step? I look at all these nodes here. This is very important. I look at all these nodes. B and G, the ones that I've just updated in addition to everyone else. I look at all these nodes and I choose the node that has the smallest label to be my next permanent node. What is the node that has the smallest label here? That's why I'm marking this as permanent, and I will stand here in the next iteration and I will repeat exactly the same things but standing at B. So how does this step work again? After I've updated the labels, I look at all the nodes, I look at all the labels. So B has a label of 2, G has a label of 6, everybody else is still infinity. Everybody else is still infinity. So the smallest label among them all is B. However, when I choose the smallest label, of course, I don't have to consider the one that was permanent already. So if a node is permanent, I never go back and I never consider it again. So B is the next node that I stand at. What do I do now with B? I do exactly the same step that I've done with A. So I'm checking the neighbors. Here I have a neighbor, and here I have a neighbor. So C is a neighbor of B, and E is also a neighbor of B. Now, how do I update the label here? This infinity will change, and if you will, I can go back to the red color. So this infinity will change. what will be the new value here? The new value will be 7 plus 2. What is this 2 here? 2 is the total distance from the source until here. Later on, I may be further away, so it's hard to keep basically tracking the path itself, because the iterations of the algorithm are just for updating the labels. After I finish everything, I will just read these labels and I will find the path. So while I'm working with the Dijkstra shortest path algorithm, I don't have to focus at all on what is the path itself. So I have a new link here. Since I'm standing at B, I have an outgoing link that goes to C, and that outgoing link has a distance of 7, and the previous distance was 2. This 2 in the label is the total distance from the source until here. So if this is the total distance from the source until here, if I add the 7, it becomes the total distance from the source until C. So 7 plus 2 is 9, so the new label becomes 9, comma, 9, comma what? 9, comma B, exactly, because I was standing at B, so if I'm discovering a path that reaches C, the node before me is B because I was standing there. What is the other node that I can update the label for? Here, node E, 2 plus 2 is 4, so this new label becomes 4, comma, B. So I just finished this step. I repeated the same step of A. I was standing at B. I checked the neighbors only. Focus, the neighbors only. I updated the labels. What do I do next? Again, I repeat the same step of looking at all the labels. I look again at all the labels except the ones that are permanent. B is permanent. I'm done with it. A is also done. So I look at all the other labels and I choose the smallest one to be the next permanent node. So what is the smallest label? Here I have a 9, I have a 4, I have a 6. So 4 will be the next permanent node. So E will be the next permanent node. Question, does the next permanent node have to be among those that I've just updated? So in the previous step in which I was standing at B, I updated C and E. Is it necessary that the next permanent node is one of them? No, it could be another one. So if these numbers are different here, if this distance was 3 here, if this distance 6 was 3, this label would have been 3, and 3 would have been better than 4, so G would have been the next permanent node. This is not confusing or anything, because at the end of the day, as I informed you at the beginning of this video, as an outcome of the Dijkstra shortest path algorithm is not just one path from A to D, although this was our target. However, as a byproduct, I'm getting all paths from A to B, from A to C, from A to D, from A to E. So basically, while I'm doing this algorithm, these iterations of updating labels and going to the next permanent node, I'm actually exploring many paths at the same time. I'm exploring many paths at the same time. So it is possible that after I stand at B, I go to G directly, and this case will come up. So let's just ignore it for now. We figured out that the next permanent node is E because it has the smallest label among them all except the permanent ones, right? So what do I do next? I stand at E and I repeat exactly the same procedure. If I stand at E, what do I do next? I check the neighbors of E. What are the neighbors of E? F and G and B. B will not be changed because it was permanent already. I never go back. Otherwise, I will just increase the distance. I never go back. So let me check F and let me check G. Now, the new label for F, let me change color to red again. The new label for F will be 2 plus the previous label, which is 4, which means 6, comma, E. I'm standing at E. Do you see this label, which I've used here to define the meaning of the labels in the first place? Do you see this label 6, comma E? At that time, I've just updated this label, and what this label means again is the following. The shortest path discovered so far from the source until our node F has a distance of 6. So the shortest path discovered so far from the fixed source until F has a distance of 6, and this path is coming from E. So the node previous to F was E. What is the other neighbor? The other neighbor is G. Let's check the new label here. So if I take 1, which is the distance of the new link, plus the previous label, which is 4, 1 plus 4 is 5. Is 5 less than 6? Yes, 5 is less than 6. So that's why we have to change that label. So although I had a label with value 6. Let's change this label into 5, comma, E, because I'm standing at E. Now, what does this mean exactly? It means that along the process of the algorithm, I had discovered a path from the source until E, and that path had a distance of 6. Now I'm discovering a better path from the source until E, which has a distance of 5. The first one was coming from A directly. Sorry, I'm talking about G. Again, the first label 6, comma A says the following. I had discovered a path from the source until G, which has a distance of 6. Now I'm discovering an alternative path from the fixed source A until G, which has a shorter distance, 5. That's why I just take away the previous path and I consider the new path, in other words, the new label. Now, I have finished now updating the neighbors. I was at E here. I updated the label for F. I updated the label for G. I cannot update the label for B because it was permanent already. So I'm done with updating the neighbors, updating the labels of my neighbors. What do I do next? I do that step of checking all labels and choosing the smallest one to be the next permanent node. Remember, I'm looking for the shortest path, so let's choose the smallest neighbor, the smallest label as our next permanent node. Now, what are the values of the remaining labels? So all labels except the permanent ones. Here we have a 9, here we have a 6, here we have a 5, and everything else is infinity. So what you see here, G becomes the next permanent node. So I stand at G, repeating the same process, repeating the same iteration of checking the neighbors. Now, what are the neighbors of G? A is a neighbor, but it was permanent. I don't change it. E is a neighbor. It was permanent. I don't change it. Now, H is a neighbor that can potentially change. So what will the value of the new label of H become here? So the infinity will be taken away, and the new value will be this 4 plus this 5, which is 9, comma what? 9, comma G exactly. Why 9, comma G? Because I was standing at G. Always, comma, the node that I'm standing at. And again, over and over again, I'm repeating what this label means is the following. The path discovered so far from the fixed source until this node H has a total distance of 9, and that path is coming from G. So the preceding node to H is G. Now, do I have any other neighbors to update? No, I don't have any other neighbors to update. And what we do next is to look at all the labels except the permanent ones to choose the smallest one as the next permanent label. When I was standing at G, H was the only label that I have changed. However, I don't go there as the next permanent node. I don't go there as the next permanent node. No, I'm not doing this. What I will be doing correctly is to look at all the labels except the permanent ones to choose the smallest one as the next permanent node. So here we have a 9, here we have a 6, here we have a 9, so we go to the 6. So this is the case that I meant here, and make no mistake, this is not incorrect, this is actually correct. Although I was standing at G and updated H, but the next permanent node is F, and this can be justified as follows again. Let me repeat again. It can be justified using the fact that I'm not exploring only a single path from node to node. No, I'm actually exploring many paths at the same time. So I'm standing at F. What should I do now? Exactly the same iteration. Again, checking the neighbors. What are the neighbors of F? C is a neighbor, H is a neighbor, and E is a neighbor, but E was permanent already, so I never go back to it. So I can possibly change the labels for C and for H. Let's check C. What would be the new label of C if I change it? 3 plus 6 is 9, which is the same as this 9. So it's up to you. We may leave the label as it is, or we may change it. Or if we have a second criterion to break the tie, we could have used it as well. However, for simplicity, if the label is the same, let's just leave it. Now, what does that mean again? What it means is that at the beginning, at some time during the iterations of the algorithm, I discovered a path of total distance 9 from the source until C. Now I'm discovering another path from the source until C, also with a distance of 9, but it's a different path. So either I adopt it or I leave the first one. Let's just leave the first one. So bottom line, we don't change this label because the new one had the same value, 9. So let's just leave it because the new label is not smaller. Now I'm standing at F again. Let's check neighbor H. What would be the new label here? 2, which is the distance of the new link, plus the previous label 6. 2 plus 6 is 8, and 8 is smaller than 9. So I must change this label into 8, comma, F. I'm standing at F, so it's 8, comma, F. Again, what does this mean exactly? It means that at some point, I discovered a path from the fixed source to H, which has a distance of 9. Now I'm discovering a shorter path, so we have to adopt it. The label becomes 8, comma, F. By the way, when do we stop? When do we stop the algorithm? Let's make this comment, and then let's go back to continue the algorithm, and we will do everything that you want. Now, we stop if the question is find the shortest path from A to D. If this was the question, we have to keep going until D becomes permanent, until that destination becomes permanent and I stand there, if this was the question. However, if the question is find the shortest path from A to everybody else, so if the question was find all these paths all together, then we have to keep going until every single node becomes permanent. So we have to keep going with this algorithm until all nodes are covered, until all nodes are permanent, until I have stood at every single node in the network. So let's go back to our iterations, to our algorithm operation. We were at F, right? We were at F. We updated the label for H. The label for C was not updated. We don't have another neighbor because E was permanent already. I cannot go back there. And I'm done with this iteration, basically. And the next step is to look at the remaining labels. All labels except the permanent ones. All labels except the permanent ones, to choose the smallest label as the next permanent node. So 9 and infinity and 8. What is the smallest label? It is the 8. So this becomes our next permanent node. I stand here, repeating the same step again. What is that step? I stand at the node and I check the neighbors. Neighbors, again, are nodes that are directly connected to the node I'm standing at, which is D here in this case, D and F. However, F was permanent already, so I don't go back there. So the only node that can potentially change labels is D. Since it's infinity, since it was infinity, it means it will change for sure because any number will be smaller than infinity, and the new label will be 2 plus 8. Again, what was this 8? 8 was the total distance from the fixed source until H, regardless how it's going. I don't know that yet. I'm not really following that. I'm just working with the labels, right? And this is the interesting thing about the algorithm. I'm just working with the labels. So 8 is the total distance from the fixed source until H. 2 is that new link. So if I add 2 plus 8, it gives me the total distance from the fixed source until D itself. So 2 plus 8 is 10. 10 is less than infinity. So the new label becomes 10, comma, H. What does this mean exactly? It means the following. I've just discovered a path from the fixed source A to this node D, which has a total distance of 10, and this path is coming from H. So the preceding node to D is H. That's where this path is coming from. Are we done? No, we're not done, because the destination is not permanently labeled yet, and the other nodes are not permanently labeled yet. So let's continue. Since I've just updated the neighbor, what is the next step? I look at all nodes labels except the permanent ones. These ones are permanent, and these two are the only remaining nodes that are not permanent yet. So I choose the smallest label, which is 9. This is 9, and this is a 10, right? This is covered already, so we have only 9 and 10, and the smaller one is the 9. So node C becomes the next permanent node. What do I do next? I check the neighbors. How many neighbors do I have for C? I have D, I have F, I have B. However, B and F are permanent already, so the only one that can be updated, that can be potentially or possibly updated, is D. Let's check if we will update it or not. If I update the label for D, what would be the new label? I have the 3 plus the 9 is 12. 12 is bigger than 10. Right, which means I should not update this label. It has to stay as 10 because that path that was discovered previously is better than the one that I'm trying to discover now, so the label does not change. Bottom line, haven't you noticed that we don't change the label unless the new label is smaller than the existing one? So this is definitely important, and it is one of the famous mistakes that we sometimes see. So the neighbor's label will not change, so we can go to the next step, which is check all the labels. Check all the labels except the permanent ones to be the next permanent node. And since I have only one left, it means I have to choose it because everybody else is permanent. And this is my next permanent node. What do I want to do now? Check the neighbors. Do I have any neighbors? No, I don't have any neighbors because everybody else is permanent already, which means I'm done with my algorithm. So the labels that you see now, 2, A, 9, B, 10, H, 8, F, 5, E, 4, B, and 6, E, these are the final labels that reflect the best paths. Now, these are the labels. The labels basically contain the length of the path. So what this label says here, if I assume that D is my intended destination, this is my destination of interest. What this label says is that the shortest path from the source until this destination, D, has a distance of 10, which is a path that I did not find at the basically motivating procedure of trying to find the path just by inspection. I did not find a path that has a distance of 10. I found one that has distance of 12, another one with distance 12, and then one with distance 13. Maybe if I looked hard enough, I could have found it. However, we should not be searching for paths like this by inspection, simply because if you have a network with hundreds of nodes, that would be impossible just to inspect everything. It's impossible. However, that algorithm that you have seen is systematic and it can be implemented. You can write a software, you can write a program that does that for any network, right? For any graph that is given to you. Let me go back to this label. This label says here that the distance is 10. So the best path from A until D has a distance of 10. Has a distance of 10. However, what is this path itself? It does not say, the label does not say. However, the label tells me where is this path coming from. So what we should be doing is the following. We should be constructing the path backwards here from A to D. So the destination is D. What is the node before from the label? It's H. What is the node before here? Since this says H, we go to H and the node before is F. So what we're doing is that we are tracing the labels backwards from the destination until we come to the source and then we stop. So this is the best path. So F here, let's go to F. The previous node is E. And when we go to E, the previous node is B. And when we go to B, the previous node is E. Sorry, let me just remove this and put it in the right location. So let me repeat it again. Here, if the destination is D, so I'm talking about, let me put some lines here so that we don't get confused, because I will be finding all these paths, not just the path from A to D. As you have noticed, as a byproduct, I will be able to find the shortest path from A until every other node, right? By doing the same algorithm, by just applying this algorithm once, I'm not just finding the path from A to D, I'm also finding the others, as long as I continue with the algorithm until every single node is permanent, right? So D is the destination. The label says H, so H is the node before me. H's label says F, so F is the node before me. The label of F says E, so E is the node before me. The label for E says B, so B is the node before me. And the label for B here says A. A is the node before me. As long as I reach the source, I stop. So in short, what is the shortest path from A to D? Using this algorithm, using this systematic approach, we never had to inspect all possible paths. So by inspection was not used at all, but automatically I obtained the path A, B, E, F, H, D, right? Let me just change color here. Let me show you this path. A, B, E, F, H, D. What you see here is supposed to be the shortest path from A to D. Let's check the length of this path. 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10. So this path is actually shorter than the others that we tried to inspect. And according to this algorithm, it is not just shorter than the others that we inspected. It is in fact the shortest one among all other paths, right? Now, let's go to the other nodes. What is the shortest path from A to B? Again, we start with the destination, and then we follow or trace the labels backwards. The label of B says A. Since this is A already, so this is the path from A to B, this direct link. There is no other shorter path between A and B. What about from A to C? Let's check the label for C. Let's put the destination C first. Let's put the destination C first. The label says B, and then the label of B says A. So this is the shortest path from A to C. A, B, C. There is no other shorter path. There could be some other paths that have the same length, 9, and this is something that we came across in the basically run of the algorithm, in the process of the algorithm. However, we did not adopt it, so this is our best path, just A, B, C. A to D is done. What about from A to E here? So we start with the destination, and then we check the label. The label of E is B, and then we go to B. The label is A, and I'm at the source, so the path is ABE, right? What about from A to F? Let's go to F here. I put F first as the destination, and then we construct the path backwards. The F label is E, and the E label is B, and the B label is A. So the path from A to F is A, B, E, F. A to G here, A to G. G is the destination. Let's check the label. The previous node is E. The label is E. And then if we go to E, the previous node is B. And then if we go to the label of B itself, the previous node is A. So the full path from A to G is A, B, E, G. Finally, from A to H here, this is our final node from A to H. So again, we start with the destination, and then we trace the path backwards. The label says F here. The label of H says F, and then we go to F. The label is E, and then we go to E. The label is B, and then we go to B. The label is A. Once you have done this, this is supposed to be the final answer. So these labels here and how they evolved, how they were updated, this represents the running of the algorithm. This represents the application of the algorithm itself. Once I finished, once all nodes became permanent, I just stand at my destination. I start with my destination, and then I keep checking the labels backwards, constructing my path backwards until I reach the source. So what you see here is basically the final step that we have to do. Once we are done with our labels, once we have our final or optimal labels, I just trace these paths backwards so that we construct the path. Now I know all shortest paths from A. A is fixed. Again, let me clean this up a little bit. Our source node was fixed. Everything was based on the fact that A is the source node. So this calculation that you have seen, this computation that you have seen may represent a computation done by router A itself to calculate the best path from its own, from A itself to everybody else. Now, once we applied Dijkstra shortest path algorithms, the Dijkstra shortest path algorithm, and I know all shortest path from a fixed source to every other possible destination. If this calculation was done by router A itself, isn't it possible that router A updates its routing table? Of course, this could be the ultimate objective. Why is router A calculating the shortest paths? Because it wants to come up with its routing table. Now, again, assuming connectionless services, in the connectionless or in datagram services, how does the table look like? The table has two columns, the destination versus the next hop. In the destination, we put all nodes, A, B, C, D, E, F, G, H. These are our routers in this network. Now, for each destination, we need to find out what is the preferred next hop towards the destination. Since I calculated the paths already, I have just to go to these paths and pick up the next hop. The next hop is just the node after the source along the path. So if the destination is B, the next hop is B here because the path is AB. The path is just AB. So obviously the next hop after A is simply B, right? And A, I'm talking about the table for A, so A as a destination is irrelevant, so the next hop here is empty. And if I go to C, if C is my destination, what is the next hop? It is B as well, right? It is B as well. So bottom line, to come up with the next hop, do I have to look at the label? No, the label gives me the node before me on the path, the node before the destination on the path here. For example, if D is the destination, the node before D is H. However, the next hop that goes to the routing table is the node after the source. So if we have a long path, this node and this node might not be the same. So the only way to come up with the next hop basically is to look at the path itself. So for destination D here, the next hop is B. For destination E, the next hop is also B. For destination F, the next hop is also B. For destination G, the next hop is B. And for destination H, the next hop is B. This is just a coincidence. The next hop for all destinations will just B, and this is just coming from the paths that we have obtained. It just happens that because this link here is too long, it has a distance of 6, this link was not chosen in any one of these shortest paths. However, if we change this number to anything else, for example, and we repeat the same algorithm, these paths would be different, which reflects basically in the final routing table or the updated routing table at A. And you might see here in the next hop a combination of a B and a G. Obviously, if A is the node, the next hop is definitely one of the neighbors. In short, if I want to reach any other node here, I have to go first through one of my neighbors, and these are the possible next hop. According to the numbers that we have in this question here, because this distance was 6, and according to the paths that we have calculated automatically without any intuitive thinking, it just happens that the next hop for all destinations, it is just B. And what you see here would be the routing table that can be used by router A, right, until router A repeats the whole procedure again. This summarizes the video, and this finishes basically the description of the Dijkstra shortest path algorithm. Assalamu alaikum, and see you next time.